Well, good afternoon, everybody, and welcome to the third and final webinar today from Smart Vision Europe, where we're looking at how to interpret significance tests. And we're going to be looking at the background of significance testing, the history of it, and looking at different techniques within SPSS statistics that allow us to access and make sense of significance testing in general. If you haven't joined in these sessions before, then you should be aware that we do record them, so you'll be able to listen to them again afterwards. There is quite a lot of slideware in this session because, of course, we were talking a lot about the theory and the background to significance tests or tests of significance. So we will be sending out an email to you that allows you to download the slides. And if you find it particularly useful and you think other colleagues might have found it useful as well, but they're unable to attend, then it may be possible if you can get enough of them together for us to arrange a rerun of the session on a private basis. The best thing to do is just to ask us. And with regard to asking questions, all the lines are muted, so we ask that you use the chat panel and we'll try and keep abreast of them. I'm actually joined online by my colleague Rachel. She'll be looking at to keep an eye on the chat panel as we're going along. But we are used to people emailing us afterwards with follow-up questions as they occur to them. And we would encourage you to do so. Don't at all be afraid to do so. We're quite happy to answer questions offline. So if you don't know who Smart Vision Europe are, we're a accredited partner to IBM, a gold accredited partner to IBM. We're a technology provider. We're also a partner to Predictive Solutions and to Data Robot, and we specialize in statistical analysis in technologies with analytics at the heart of them, data science and AI. We also work, of course, with open source technologies such as R and Python. And we're a relatively small organization made up of people with quite deep experience in the software and technology space around analytics and data science and statistics. And that means that we've got lots of experience down the decades of applying exactly the techniques and the methods that we're going to be talking about here today across many different sectors and across many different applications within those sectors. Indeed, many of the sectors that you work within. Um, we will almost certainly have had experience of doing consultancy within those areas and showing how we can apply things like significance testing to those workspaces. Um, our agenda today is to start off talking about the term significance testing and the background to that, where that comes from, and then introduce you gently to the difference between the descriptive statistics and inferential statistics and how inferential statistics is linked to significance testing before we move on to interpreting probability values within the context of significance testing, sometimes called p-values. And then we're going to look at three different applications. One is looking at pairs of categorical variables, when you're looking at relationships between categorical variables, how you can do that using crosstabs and chi-square. Then we're going to look at relationships between continuous or scale variables, number variables, and how we can use correlations to make sense of that, and why the term significant here is particularly troublesome. And lastly, we're going to look at interpreting confidence intervals because that allows us to cross off when we're looking at relationships between categorical and scale variables. And confidence intervals is a good route into that world and forms the basis to other types of statistical analysis such as t-tests and ANOVA. So let's begin with the term significance itself and where that comes from. It is a troublesome term, I think it's fair to say. It is associated with R.A. Fisher, Sir Ronald Fisher. He introduced the phrase tests of significance from his seminal book, Statistical Methods for Research Workers, published in 1925. So other things that he introduced was the concept of hypothesis testing and also the concept of what's called an alpha value. But the problem here is that when we use the term statistically significant, it is likely to be misunderstood, and it is a much abused term. You do hear even politicians saying, there's a statistically significant relationship between these two factors. I think that the issue here is that in common parlance, something which is significant means something which is notable, and something which is important. It's actually quite easy to get things or find relationships which are statistically significant, but they're really trivial in nature. And where the differences between groups is quite small, this is called an effect size. An effect size is when something has a big effect on something, well, it's a way of measuring the degree to which something has a big effect on something. It's very easy to get a relationship or to find a relationship in data which is statistically significant with a very small effect size, where the difference is really small, where left-handed people are ever so slightly more likely to bet more than right-handed people, let's say in a game of cards. It's vaguely interesting, but it's statistically significant, but it's not necessarily notable within the common parlance of that. So significance does not mean notable. Indeed, sometimes it doesn't even mean it's reliable. There is an issue currently, it's well known within certainly social sciences called the replicability crisis. That means when people have been trying to reproduce the significance tests that have been carried out in classic studies and finding out that they're getting quite different results. So significance values can vary from one sample to the next, and in fact, that's in the very nature of the technique itself, of the paradigm. Indeed, even the term test is slightly problematic, I would say, because we tend to think of tests, we tend to think of something which is fairly, fairly exacting, something which is it's just going to give us a result, yes or no. We've detected something here, we haven't detected something. With significance tests, what you're doing is you're just making an estimate. So if you were trying to come up with a phrase which would describe a typical significance test, you would say it was a probability of evidence estimate because it is literally giving you the probability of evidence and it is an estimate of that probability. But I don't expect that to take off. I don't expect people to start using that. But if you as a phrase, but if you're talking about what it's doing literally, that is what it's doing. It's deriving a probability of evidence. Now, the people who are responsible really for the world of significance testing, there are a number of statisticians out there and academics out there. But if we were to boil it down to a core group, there is this relatively small group which are really responsible for a lot of the terminology, nomenclature around the world of inferential statistics, what we call inferential statistics and significance testing. So if you've heard of phrases like maximum likelihood or confidence intervals or null hypothesis or alpha levels or Z tests or anything like that or F tests, it's usually these guys that's associated with, particularly Fisher, which is where who gives rise to the term F test, Fisher test. Carl Pearson, you have Pearson's chi-square and Pearson's correlation. These are really fundamental statistics which are used, every single day by hundreds of thousands, if not millions, of people worldwide. Egon Pearson, who's Carl Pearson's son, and Egon Pearson had a colleague that he worked with, Jerzy Neyman. So Egon Pearson and Neyman really came up with the concept of things like 95% confidence intervals, etc. And they didn't necessarily all agree with one another. They certainly Pearson and Fisher, had their own bust ups over the years. Um, and as a result of that, it's the approach that statistics takes, this school of statistics takes, is kind of a smorgasbord. It doesn't fit quite together as neatly as it should. There's, it's not, as statisticians like to say, it's not an exact science. And I think that's one of the things that people find frustrating when they start to get deeper and deeper into it, is that, there's no exact way to do this, but that's possibly because in the nature of the thing that we're dealing with is data and uncertainty. When we're looking at data, we could just be looking at random information, or we could be actually seeing what's called the signal in the noise. So, it isn't an exact science, and there are certain reasons for that people have come up with different methods to try and achieve similar sorts of outcomes or deal with similar sorts of problems. Now, this approach, this sort of school of thought, if you like, for this type of statistical analysis that most people are taught is referred to as the frequentist tradition. People might not necessarily know that when they're doing a 101 stats course at university, that they're actually learning frequentist statistics, but that's what they're learning. And one of the reasons why frequentist statistics became popular was because these guys came up with techniques which allowed you to calculate a lot of the statistical analyses and a lot of the p-values associated with statistical analyses by hand. They didn't necessarily need to use a computer for that. So hence having its roots back in the 1920s, 1930s. So that leads us to inferential statistics and significance tests. To understand this, we must understand the relationship between a sample and a population. Now, a sample, I think we all understand what a sample is. A sample is when you go and you grab some data, you're taking a sample of information. You know that you can't necessarily, get all the data from all the people at one time. So you take a sample. And a statistic, the term statistic, meaning state, if you like, is a characteristic of a sample. So it's used technically within the world of statistics as something which refers to a sample of data. And the theoretical well from which a sample is drawn is called a population. And I say theoretical because it often is, effectively theoretical in the sense that, we can't know all the information about all the people. When we have a value, if we were able to come up with a value or calculate some sort of measure from a population, and we knew that measure was absolutely 100% correct, then that would be called a parameter. And a parameter is a characteristic of a population. So statistics are derived from samples, parameters are derived from populations. And in many ways, both of them are sort of theoretical. Think of it like this. Think of it like the Indian Ocean. It's a vast ocean. Even if you were able to precisely determine its limits geographically within, centimeters, something like that, even if you were able to do that, if you wanted to calculate like salinity or average temperature or something like that, you'd have to really have all of the information available to you. Because, of course, if you take a sample from the Indian Ocean and you take a sample from another location in the Indian Ocean at a different time, you're going to get ever so slightly different values. So the parameter, meaning what is the average salinity or what is the average temperature, is really theoretical because it's impractical. You can't really ever get to it. So the population being the ocean, the sample being literally the sample you take, the test tube, the parameter being the theoretical true value of the thing that you're trying to estimate, and statistic being the value that you calculate from a sample. So statistics are therefore used to estimate parameters, to make a guess or to make an estimate of a parameter. And obviously, the larger the sample you have, the more representative a sample you have, theoretically, the closer that should be, or the better an estimate that should be of a parameter. So that's the theoretical background from that. So we're using statistics to make an inference, to infer what a parameter value is in a population. How can we do this? Well, of course, as we say, we can take samples, and we can take samples and we can calculate probability, or sorry, we can calculate these statistical values from them. And we understand, at least intuitively, that if we take repeated samples, that the statistics themselves might vary slightly from one sample to the next. So, for example, if you were trying to estimate the average age of men and women in some sort of population, might be a nation or something like that. It is unlikely that even with modern technology that you're going to have exactly all the information about all the people in that population at that exact point. You're probably going to have pretty accurate information. You're probably going to be able to calculate it pretty accurately. But let's say you're trying to take it to like 16 decimal places. You're never going to get exactly accurately. So you draw a sample, and you find in one sample the men are on average age 34 and women are aged 32. Take another sample, you find that the difference is different, that, men are aged 33 and women are aged 30. Another sample is the opposite way around. It's actually the women are aged on average 32 and the men are aged 31. So samples vary from one to the next. And that's an issue. And that's a problem for us because we'll never know the true parameter value. It's a kind of an unknowable thing. And furthermore, that when you take a sample, they vary from one another, and the reliability of the sample may vary depending on how representative it is and how big the sample is that you take, how many records you have within it. So in that sense, statistics is the science of variation. We're looking at variation here. We're looking at variation within samples. So we're looking at how much ages vary within a sample. But we also have to bear in mind that samples vary from one sample to the next between. So within samples and between samples. We might, for example, start to postulate the notion that the mean ages are in fact exactly the same in the population, and that the differences that we're observing in our samples are actually illusions. They are an artifact of the fact that the samples vary from one another, that they're merely estimates. I mean, the ages here are quite close together. They're not massively different from another. We don't know what the sample size is here. It could be like 100, it could be like 50 people. We don't know. But it is possible that, in fact, they're the same in the population, and indeed, many people would say that that's the kind of thing you should be testing for. You should be testing at least to find out whether or not the difference even exists. In statistical testing, this would be known as effectively a two-sided significance test. It's one where you're saying, I don't assume that men are older than women or that women are older than men. I don't assume that. In most populations, on average, women are slightly older than men because they tend to live longer. But let's just say, for whatever reason, we're not making that assumption here. We're just saying that we think that there might be that there might be a difference between the mean ages, and we're not saying which sex is older or younger than the other. So that would be a two-sided significance test. If we were guessing that women were older than men, let's say that would be a one-sided significance test, and we could test against that probability. But here we're just saying, look, maybe they're exactly the same in the population, and any differences that we observe are purely random. So where does significance come from within this context? Well, significance does not mean noteworthy. Instead, these tests simply might indicate that the evidence that we're collecting does not support the assumption there's no difference between certain groups in the population. And this is going to be measured by a probability value. This is how we're going to make this assessment. We're going to choose a p-value. We're going to say, what's the probability? Effectively, we're going to say, what's the probability that the differences we're observing here have occurred due to random chance. And that probability value, when you do a statistical test in a tool like R or like SPSS or SAS or Minitab or Stata or any tool you like, is labeled, and it's labeled differently, often depending on one test to the next, but it's interpreted the same way. So I just need you to understand that when it says SIG, it means significance test. When it says P, it means probability. When it says prob, it means probability. And when it says asymptotic significance, it means probability. They're interpreted in the same way. So don't be fooled by the labels they're given them. A value of 0.001 in a significance test, or P value, equates to 0.1%, a 0.1% chance or 0.1% likelihood. Whereas a value of 0.172 equates to 17.2%. And the probability value of 000 does not mean zero, does not mean there's no chance. It never means there's no chance. It just means that there aren't enough decimals to display the true probability. And in SPSS, if you want to see the true probability, you have to probably double click on the cell that the probability value appears within, and it would show you, the true probability value, or at least show it in scientific notation. And a value of 0.034 would be 3.4% or 3% if you're rounding it. So that's the first thing. Don't get fooled by the labels. They're all interpreted in the same way, and every probability value can be converted into a percentage if that makes it easier for you to interpret it. So when we return to our example here and we carry out a number of tests, the type of test that would be appropriate to compare two averages drawn randomly from a population, particularly a population where we're looking effectively at a sort of a random sample, a fair random sample. If we're comparing two averages, we'd normally do a t-test. And the t-test here would return to us different p-values. So if we looked at the first one here, it gives us a p-value of 0.111. That's saying that we would see a difference as big as the one that we're observing here of 34 and 32, just 2 years, as big as this 11% of the time randomly, effectively. Or if we saw a difference here of 3 years, maybe this is a bigger sample, it's a bigger difference, we'd see a difference as big as this 4% of the time because the p-value is 0.04. And here we've seen a mean age difference of just 1 year. And it's so small, we'd say a difference as big as this 33% of the time. This is how we would interpret the p-value if we were able to run the test again and again. So this relates to this notion of hypothesis testing. Just got to link this up. Now, I said, if you're investigating a relationship to begin with in statistics, it's usually because you're curious to see if there is a difference or a pattern or a relationship. Okay? In other words, you have some sort of hypothesis. There has to be some sort of statement that you're making, and you're going to say this probability links to that statement. For example, if I think there is a difference between the average age of men and women in a given population, this is actually referred to as the alternative hypothesis. This is my hunch, if you like. And it's given the label H1 in the scientific notation. But in reality, our statistical test doesn't look at the hypothesis, the alternative hypothesis. It looks at the thing called the null hypothesis. So in reality, you're testing to see if your data supports the idea that there is no difference between the average ages of men and women in the population of interest. And this is called the null hypothesis, or H0 in the scientific notation for short. The p-value test then calculates the probability that indicates to us if the null hypothesis is true, how often would we get a result as extreme as the one we observe? That is literally how you interpret a p-value. How often would we get a result as extreme as the one we observe if the null hypothesis is true? So it's almost, we go back to these examples here. We're looking at this one here, difference of 33 and 34. Let's say it's a sample size of, I don't know, 100 people, 100 males, 100 females, something like that, and we're getting a p-value of 0.04 there. It's saying that assuming you're living in a world or a universe where in this population the men and women actually have exactly the same average age, you could still come up with a sample where the difference was as big as this, 3 years, and you would see that difference 4% of the time randomly. So we're saying that the probability of getting a result as extreme as the one we observe is 4%, even in a world where the null hypothesis is true, even in a universe where it's true. So that's how we make sense of it. So at what point do we say we should accept this null hypothesis? We say, yeah, we're happy with that. We're happy with the idea that there's no difference between men and women in terms of the mean ages in the population. Or we reject it. We say, no, look, there isn't enough evidence to support that notion. That means we have to choose a number. So we could choose a p-value of 0.32, and we say, well, look, if it's less than 32%, we'd say if there's less than 32% chance that the two ages are in fact the same. If you only see it 32% of the time, if you only see a difference as big as that 32% of the time, we're going to reject the null hypothesis. Does that seem reasonable? Well, most people would probably say it isn't, but so maybe we could be a lot more strict, and we could say, okay, let's say it has to be less than 0.0001%, so less than like 1 in 100,000 or 1 in a million or something like that, before we say we reject the null hypothesis. You've got to choose a number at some point. You have to choose some threshold. And in fact, that threshold is called an alpha level. And it's pretty arbitrary. There's no science to it. It's just somebody drawing a line in the sand. And of course, it goes back to Fisher again. Ronald Fisher said that 5% or 1 in 20 chance was a reasonable level to choose. So this p-value became 0.05. And for decades after that, that is the level that most people in social sciences in particular work towards. If the p-value was less than 0.05, they rejected null hypothesis. And if it wasn't less than 0.05, they didn't reject the null hypothesis. Now, in fact, if you look at what R.A. Fisher said, he said that rather than just rejecting the null hypothesis at p equals 0.05, he said, if 1 in 20 does not seem high enough, we may, if we prefer it, draw the line at 1 in 50. 2%, that would be p equals 0.02. Or 1 in 100, that would be p equals 0.1. Personally, the writer prefers to set a low standard of significance at the 5% point and ignore entirely all results which fail to reach this level. A scientific fact should be regarded as experimentally established only if a properly designed experiment rarely fails to give this level of significance. He might well have said it should be at a 1% point, but people agreed with the 5% mark. Why? Because it's a round number. It's utterly arbitrary and it has caused issues in the past. It's not a magical certainty that the relationship you're observing really exists in reality, nor is it a certainty that it doesn't exist in reality, you know. So either way, it's just a line in the sand. It's just an arbitrary cutoff point, and you always have to keep that in mind, that if you do statistical analysis, you will find situations where the p-value is less than 0.05, and it's almost certainly a spurious relationship. And at the same time, that is called a type 1 error, by the way. And at the same time, you will find situations where there doesn't seem to be a difference between two groups, and there is a difference between two groups in reality. Other analysis shows that this is the case. And that is called a type 2 error. So it's just a reality that this isn't exact. It doesn't know. It's based only on the data you have. And then sometimes, you know, people do win the lot. Somebody won the lottery twice recently. It can happen. It's never saying it won't happen. Okay, therefore, the alternative hypothesis is there for reference only. It turns out, actually, you never accept or reject it based on our analysis. In fact, we never even accept the null hypothesis. The most we can do is not find enough evidence to support it, and therefore we reject it. And some analysts argue this is a real limitation of classical or frequentist statistics, this whole school of thought. A completely alternative approach to hypothesis testing can be found in Bayesian statistics, where we compare how much evidence there is for the null hypothesis versus the alternative hypothesis. It doesn't use p-values. It uses a ratio. It uses this Bayes ratio. It basically says how much evidence there is for the null versus the alternative. And we've got a little video on that. You can check that out. So the point here is that you will see people saying, so we accept the null hypothesis. You don't accept the null hypothesis. You know, so you hear people writing things like, oh, therefore we accept the alternative hypothesis. You don't accept an alternative hypothesis. The only thing you can do is either reject the null hypothesis or not reject it. It's entirely one-dimensional. That's the only thing that it shows. Now, contrary to a lot of statistical teaching, they say the p-value does not indicate the probability that the null hypothesis is true, nor does it indicate the probability that the data were produced by random chance. What p-values can do is indicate how compatible or incompatible the data are with a null hypothesis. That's all it's doing. So this is probability of evidence estimate that we used, this term that we used earlier on. Now that might sound like semantics, but it's not. And the reason is simply that the probability of x given y is not the same as the probability of y given x. So if you ask, what's the probability of somebody having a full driving license given that they're age 17 or over? And you think to yourself, well, this person's age 17 or over. What do you think the chances are that they've got a driving license? Well, I don't know, maybe it's 60%, 70%. Well, I don't know what proportion of people who are adults and say age 17 or over have a driving license. It might be 80% chance, you know, 0.8 probability. But that's not the same as saying what's the probability of somebody being age 17 or over given that they have a full driving license. Because you have to be age 17 or over to have a full driving license in the first place. So if you've got a UK driving license, you have to be age 17 or over. So it's a 100% chance that you're age 17 or over. And those two things are not the same. And because they're not the same, x given y is not the same as y given x, you need to get the language right around how you're describing the probability value that is given by a significance test. Therefore, the probability of the null hypothesis being true given the evidence is not the same as the probability of getting that evidence assuming the null hypothesis is true. And that's really what we're doing. We're saying, how often would you get that evidence? How often would you get a result as extreme as that in a universe where the null hypothesis is true? Because it can happen. Okay, the null hypothesis is pretty important in these tests of significance. To correctly interpret any significance test, you must know the null hypothesis associated with it. And different significance tests have different null hypotheses associated with it. So, for example, a chi-square test has a null hypothesis that states that the two variables are independent of one another in the population. In other words, they're not related. The t-test or an f-test, the null hypothesis for these are that the group means are the same in the population, that the two means for males and females are the same, or for three groups are the same. The null hypothesis for Pearson's correlation coefficient is that the correlation value is actually zero in the population, that there is no linear relationship. Not that it's weak, not that it's negative or anything like that, that it's actually zero. Then you have tests that test to see if your data is normally distributed, for example, and if your data has the same, if two groups have the same amount of spread with them in terms of the standard deviation. And people start to get confused over that because they think that they want their data to have the same spread, and they think that any p-value less than 0.5 is good. Well, in Levine's test of equality of variance, the null hypothesis is that the groups have the same spread. So if you got a p-value that was equal to like 0.136, it would mean that you don't have enough evidence to reject the notion that the two groups actually have the same standard deviations. And that would normally be regarded as a good thing because it would help you then go off and do what's called a parametric test. You'd say, yep, I don't have any evidence to show that these two groups have different standard deviations. In the same sense, you might do a test to find out whether or not your data is normally distributed. And in KS-Lilliefors, the null hypothesis assumes that the data is normally distributed. So if you got a p-value of equal to 0.02, you would be rejecting the null hypothesis that the data is normally distributed. And you say, I don't have enough evidence to support that. So knowing what the null hypothesis is associated with each test is pretty important. And you must know that before you even start the process and before you choose the analysis. Let's look at an example. Let's look at crosstabs and chi-square. This is one of the first ones we talked about here up here. Null hypothesis for chi-square test is that two variables are independent of one another. So I'm going to do a little crosstab for you in a minute and just show you how you can get this in SPSS. But I'm going to show you how this is calculated first of all. So crosstabs are a powerful way to examine relationships between categories. The chi-square test is commonly associated with crosstabs. Here I have a crosstab dialog in SPSS. I'm looking at the relationship between gender and employment category. So the null hypothesis that I would be testing here is that the two groups are independent of one another, that gender in no way affects employment category and employment category in no way affects gender. Well, you wouldn't expect your employment category to affect gender, but in terms of the test, it doesn't really know that. So it's just saying that the two factors are kind of independent of one another. So when we do a crosstab like this, we get a little table out, and it shows us, how many females are clerical workers, how many males are clerical workers, how many females are managers, how many males are managers. It's not very easy to interpret it, of course, because we haven't got any percentages in there. Be much easier if we added in percentages. When we add in percentages, then we can say what percentage of females, given that there's a different number of females than males, 95% of them are clerical workers, only 61% of the males are clerical workers, only 4.6% of females are managers compared to 28.7% of males. And so immediately we're seeing some quite big differences here. And we're starting to ask ourselves a question, how often would you see a difference as big as this in a world where there was absolutely no difference really in terms of women or men's likelihood to become managers or clerical workers, that there was no relationship between the two. So the way in which the chi-square statistic does this, the way in which it works it out, is it very cleverly works out what's called the expected count. So if we look at this group here, the female clerical workers, it says you got 206 of them. You would actually expect to get only 165.4. I know it seems silly to have a decimal place here, but it's saying 165.4 people in that group. if gender made no difference to their likelihood to become clerical workers. And that's because it's simply adjusting for the fact that you've got 216 females and 258 males. And it works that out by simply multiplying for each cell um, the row total multiplied by the column total. Here's the row total. Here's the column total, and divided by the grand total. And that gives you the expected count. So if you take 216, you multiply it by 363 and divide it by 474, that gives you 165.4. And you can work that out for each cell. You can work out how many you expect to get. Look, it says we've got 74 male managers. But if everything was fair and maleness made no difference to your likelihood to become a manager, you'd expect to only get 45.7. So what chi-square then does is it looks at the difference between the observed and the expected. And of course, the bigger the difference, the bigger the deviation away from what you'd expect to get, the more bias there is in the table, if you like. But if it added all of these residuals up, it would be adding 40.6 to minus 40.6, minus 12.3 to plus 12.3, and minus 28.3 to 28.3. And that would come to zero. And that would be no use to us. So what they do is they square these differences called residuals, and that's why it's called chi-square. Chi is just a Greek letter of the alphabet, meaning x. It just means x square. So performing the calculation based on the sum of the squared residuals, what it does is adds these up, allows us to reach a value where the larger the number, the less likely it is that the variables are unrelated to each other in the population. And this value is the Pearson chi-square statistic. Now, it's not quite as simple as that. It's a little bit more involved. It involves dividing the expected frequency back into it again. But suffice to say, that's the essence of it. And that gives you a number. And the larger that number occurs, the more likely, the less often that occurs randomly in the population. So the null hypothesis associated with the Pearson chi-square test is that the variables are unrelated. A small probability value, let's say less than 0.05, indicates that the differences as large as the ones observed would only occur less than 1 in 20 times when this null hypothesis is true. And that leads us to reject the null hypothesis here. So look, the p-value here is so small it can't display all the decimal places. And if we were reporting this result, it would say the chi-square test indicates that the probability of obtaining a value as extreme as the one observed is less, in this case, less than 0.01, assuming the variables gender and employment category are unrelated. Given this result, there appears to be insufficient evidence to support the null hypothesis, and it is therefore rejected. Now, if I jump back to SPSS and show you how to do that, we would go to Analyze, down to Descriptive Statistics, down to Crosstabs, and I'd look at gender. I'll put that in the rows. Employment category, put that in the top. And if I just run that, that's just going to give me a simple table. There's this simple table. Let's get rid of this output from earlier. Not very useful to me. So I run it again. I go back to it and say, look, let's add in the percentages, and I go and add in percentages. This percentages. Now that's better. Looks a bit better. Look, now we can read the differences between employee category and gender. Look, 94% of females are clerical workers. Only 61% of men are clerical workers. And if we wanted to see these residuals and expected frequencies, we can actually add them in by clicking on cells here. And we can say, look, what's the expected frequency and what's the unstandardized? That means raw residual. And we get these numbers that we saw earlier on. It's saying, look, here's the count, here's the expected count, and here's the difference between the expected count and the residual. And the larger the residual, of course, the larger the deviation from from what you'd expect to get and what you actually get. And it helps you then figure out which cells or which groups are really driving the overall chi-square test. So I want to run the chi-square test. I'm calling up the crosstabs again. I would just go to statistics here and click on chi-square, click continue, click OK. It runs my chi-square test. This is my Carl Pearson's chi-square test. The sum of the squared residuals effectively comes to 79.685. How often would you see that value? Well, it's saying it's 4.9736 minus 18 decimal places. So it's 18 decimal places back, 18 times, and then you get 497. So it's a very, very small probability that you would see a difference as large as that occurring in a sample drawn from a population where there was absolutely no difference between people's women or men's likelihood to become managers or clerical workers. It could happen. It's not going to happen very often, and therefore you would reject the null hypothesis that the two variables are unrelated to each other. Okay, that's all we're doing there. Okay, so that's us looking at our first p-value here, and we're looking at the relationship between uh, uh, categorical fields. What happens when we're looking at the relationship between um, continuous fields or scale data? Well, here we're seeing a scatter plot. We've all seen scatter plots before. The difference between the data we were looking at previously in this data set is we're not dealing with categories, we're dealing with numbers. So look, we've got salary against beginning salary. And here we've got examples of scatter plots where each point represents a car or an automobile. And here we haven't got categories, we've got physical numbers. We're looking at vehicle weight. This is called a continuous or a scale variable. Vehicle weight against horsepower, miles per gallon against time to accelerate from 0 to 60, and horsepower against time to accelerate from 0 to 60. And we can calculate what are called Pearson correlation values for these. And Pearson correlation values show us the strength of a linear relationship, how much this relationship can be described using a straight line. And you can see that this line here is much straighter, or it's trying to form a straight line much more than this relationship here. And as a result of that, the correlation value is higher. In fact, if it was perfect, if it was absolutely perfect and everything fell on exactly the same line, the correlation would be equal to 1. And in fact, we do a webinar just on correlations. You'll see a YouTube video about that if you go and look it up. We just look at correlations. But here it's really showing us the measure, the strength of the relationship. This is not a p-value. This is called an effect size. So horsepower and vehicle weight are really quite strongly related to each other because they're quite close to 1. Look at that, it's quite close. Whereas time to accelerate from 0 to 60 and miles per gallon is weaker, but it's still, most people regard that as kind of reasonably modest or modest, but, modestly strong. Zero point 0.4 correlation. Once you get above zero point 0.3, you're into the modest zone. Anything less than 0.3, most people would regard as fairly weak. Here we've got a strong negative relationship. This is time to accelerate from 0 to 60 against horsepower, meaning that the higher one value is, the lower the other value is. So the more horsepower you have, the less time it takes to accelerate from 0 to 60 and vice versa. And again, this is quite close to -1. So that's quite good. If it's close to 0, if it's just a random mess like this, like mileage against miles per gallon, then, you're going to get a very weak correlation close to 0. And you can even, I guess I just throw this in just to point out that correlations can't see bendy relationships. They can only see straight line relationships. So sometimes you'll get like a correlation which is notable, but when you actually investigate the relationship, it's actually bendy, and you'd be better off maybe transforming the data. In this case, maybe taking the square of a value or taking the log of a value to kind of straighten it out. It's a trick that relationships that statisticians do. The key here is that correlations only measure linear relationships, straight line relationships. So it turns out you can calculate these correlations in SPSS using correlation matrix. It's really simple. You just choose one variable against the other. And look, it's showing strong relationships here between things like current salary and beginning salary and education level in years and beginning salary. Look, beginning salary and current salary got a correlation of 0.88. Education levels in years, I've been bolding them here, got a correlation of 0.661, quite strong, 0.633. And the rest aren't very strong, okay? But we might be asking ourselves which ones are statistically significant, because these aren't measuring the probability, they're just measuring the strength of relationship. Well, we have to remember what the associated null hypothesis is of a correlation. And the associated null hypothesis is that the value is actually 0 in the population, i.e., there's no linear relationship. So we're not testing whether or not it's notable, and we're not testing whether or not it's strong. We're just testing whether or not it's 0. And as a result of that, when we add in the significance values for these correlations, you can get situations whereby you've got a really weak correlation. Look at this, is minus 0.097. It's what? It's point 0, zero point 0.1. It's getting close to zero point 0.1 if you're rounding up minus zero point 0.1. It's really, really weak. But look, it's statistically significant. It's less than 0.05. Whereas this one here isn't statistically significant, 0.046. It's just weak enough for it not to be statistically significant. What does this teach us? It teaches us that just because something is statistically significant doesn't mean it's notable. Is this significant? Yes, because the probability of getting a result is as, in inverted commas, as extreme as minus 0.097, assuming there's no relationship between the variables, is only 3.4%. Does that mean it's notable or worth reporting? No, not particularly. But then that's not what the null hypothesis for Pearson's correlation value is directed at. It only states that there is no relationship there at all in the population. That's what the null hypothesis is. And here we cannot reject the null hypothesis that the correlation value is. Oh, sorry. Here we are rejecting the null hypothesis that the correlation value is, in fact, zero in the population. We're saying it's probably not zero. It's, it might be zero point 0.1, but it's not zero. And that's not very strong. It's not very notable. And it's the exact perfect example of when something is significant, but it's not significant in the common, in the common sort of way in which we would use the word significant. It's not notable. If you want to know how to generate a correlation coefficient, you go to Analyze, down to Correlate, Bivariate, and you choose your variables. Look, I've already chosen them in here. It's a good idea to switch off show lower only triangle and switch off show diagonal. And these days, SPSS will even color code the correlations for you. Look, here's the significance values added in. Here's the n numbers, and here's the correlations for each pair, each relationship. There's no dependent and independent relationship here. It's just a two-way relationship. So the correlation of current salary against education level in years is exactly the same as the correlation of education level in years against current salary. Okay. So that's a good lesson there. That's showing this. P-values only show you one thing. They're just giving you the opportunity to reject or not reject the null hypothesis. They're not saying whether or not the relationship is strong or notable. That takes something else, a different type of statistic, like an effect size statistic, like correlation. Okay, lastly, we want to talk about how to interpret confidence intervals. So confidence intervals, we're returning to this notion here that we've got different samples from the same population which vary, and we've got averages here. We get this. If you repeat a survey or a project, you won't get exactly the same results every single time. You calculate a statistic and the results vary from one sample to the next. No statistical calculation can tell you what the actual value of a population parameter is because it's based on a sample. And we don't have the luxury of repeating samples over and over again. But we can estimate a range of values that it's likely to lie within. So this is something. Not all the hope is lost. And we can do this with averages, for example, by requesting things called confidence intervals. Confidence intervals can be shown graphically as error bars. They look like little TIE fighters on the side here. Here it's showing in the center of the confidence interval, it's showing the mean. And confidence intervals don't always show means. You can have confidence intervals for other things like medians and for other types of statistics, but the most commonly associated with means. And here it's showing a mean, and the upper and lower parts of this interval are showing the upper and lower confidence intervals for that mean, for that group, whatever that group is. It might be left-handed people over here and right-handed people over here. So you just need to bear in mind that they have a graphical equivalent that we can show them. Now, there's a procedure called the Explore procedure in SPSS, and it produces lots of summary measures, but it also produces for you 95% confidence intervals for a mean. Look at that. I've got age of employee. The mean age of employee is 34.74, and the confidence interval is 33.67 and 35.8. So in this example, what we're saying is the mean age happens to be 34.74. Of course, we don't know what the real mean age is for all of the employees in the entire company because we've only got maybe a sample from a particular point in time or, a particular week or a particular branch or a series of branches or something like that. We haven't been the sample everywhere. It's from population. But we don't know what the mean age for employees in the population is. We know that the sample was drawn from, but the confidence intervals indicate that is likely to be contained in a range like 33.67 to 35.8. As we know, drawing another sample would probably result in a slightly different mean value. We have to bear in mind that all our statistics are likely to vary from one sample to the next, not just the mean, however. And that means if we drew another comparable sample and recalculated confidence intervals, they too would probably be different. In other words, don't get too hung up on the values of the confidence intervals themselves any more than we fixate on the value of the mean, because the confidence intervals will change from one sample to the next, and the same way the mean does. But what we can say is that even if the intervals vary from one sample to the next, they are likely to be broad enough that on 95% of occasions they will contain the population mean. So on 95% of occasions, comparable sample of a comparable sample size, the confidence intervals will contain the mean. And I'm being really careful about this because this is one of the most commonly misinterpreted statistics that's out there, to the extent whereby I used to actually Google this live in the webinar, and the first hit that you get with Google was exactly the wrong interpretation of confidence intervals. What we cannot say is that we are 95% confident that the population parameter is between X and Y. It might be very tempting to say that. And that's because the intervals themselves will vary from sample to sample. It's the procedure that on 95% of occasions that will capture the population mean. So just be careful about that. We're actually saying that the intervals they're broad. The intervals are broad enough that 95% of occasions these intervals or intervals like this will capture the mean. Okay, I'm gonna have a look at that, how we actually do this and prove it to you. So I'm gonna click out here and I'm gonna go to open up a little data set here. I've got a little data set here where I've kind of created some simulated data. I've got this little value here called population 2. If I run descriptive statistics on that, I'm gonna run it. It's actually got just this huge number of cases. I think we've got 3 million cases in here, and the value goes from 1 to 42, and the mean is 3.333. So it's nice and easy, okay? So 3.333. So it's just so that's what the true mean is. Let me just delete some of this output here to make this clean. That's what our true mean is. So I run that. Let's put that right at the top. Our true mean 3.333. What happens if we took a sample from this data and then calculated the 95% confidence intervals? Would it capture the true mean for us? And what if we did it again and again and again and again? Well, what we would expect that 95% of the confidence intervals that we calculate would contain a value of 3.33, and that 1 out of 20 times it wouldn't do that on average. So sometimes we've done this, and it's exactly shown that if I go run at 19 out of 20 times, and sometimes it's 20 out of 20 times it's come up with the true mean value, and sometimes 18 out of 20 times come up with the true mean value. But you can see here, there's the first sample. It's only got 50 cases. And 3.33 is indeed between 2.51 and 4. Here's another one. Look at this. It's quite close to 3.33. Look at that. Second sample, but it's still within it. Third sample, 4.4. Oh, look at that. It's also very close to 3.33. There you go. There's the first one there. This did not contain the true mean. That's sample number 5, I think. Did not contain the true mean of 3.33. It's actually misestimated it. But you can see that the sample sizes are different each time. Now, on average, if we do this again and again and again, and we let it go through it, we should find that 19 out of 20 of them will come up with confidence intervals that contain the true mean. It's just running it again and again and again, taking a random sample each time as it's doing that. Now, while it's doing that in the background, we can go back and check it later. But let's just return to how this is working. What's it actually doing? Well, it turns out there is a special statistic that drives confidence intervals, and it's called the standard error. And when we're calculating confidence intervals for a mean value, we use a thing called the standard error of the mean. But there are other standard error statistics, such as standard error of the median, standard error of the difference, standard error of the correlation. But they're really useful for when you need to calculate confidence intervals for other statistics. The standard error is based on a standard deviation. We've kind of encountered a standard deviation before. This is just an average spread of the sample. But the standard deviation measures variation within a sample. And the standard error tries to estimate the variation between samples. In other words, it's telling us how much on average a mean will vary from one sample to the next, which is really powerful. So here it's saying you got a mean of 34.74. on average, with a sample size of this size, I don't know, whatever the size is, like 400 cases, I'd expect that to vary by about zero point 0.5 on average from one sample to the next. And to calculate the 95% confidence intervals, what you do is you take the standard error and you multiply it by 1.96 because in statistics, 1.96 is associated with 95% because 95% of cases in a normal distribution fall between 1.96 standard deviations above and below the mean. If we didn't multiply it by 1.96, we would be calculating 68% confidence intervals because one standard deviation above and below the mean in a normal distribution accounts for 68% of cases. And if we wanted to calculate 99% confidence intervals, we'd multiply it by 3 because about 3 standard deviations above and below the mean in a normal distribution account for 99% of cases. So that's why we're multiplying by 1.96 because that's associated with 95% confidence intervals and its relationship to a normal distribution. And when we multiply 0.542 here by 1.96, it comes out as 1062, 1.062. We take that away from 34.74, it gives us 33.67. We add it to it, and it gives us 35.82. And that's how it's calculating the confidence intervals. And that's really important because it means that the standard error is therefore only based on two values. The standard error itself is actually based on two values. It's based on the size of the sample and the size of the standard deviation, the spread in the data. So that means that smaller confidence intervals, so confidence intervals move further apart. They become wider if you've got a smaller sample and or you've got a big standard deviation. And confidence intervals move closer together when you've got a big sample and or you've got a small standard deviation. So when I look at two little sample means here, like males and females against mean age of employees, look, the males have a smaller, the intervals are closer together. Look, the little TIE fighter wings are closer together than they are for the females. Why is that? Well, it's one of two reasons. Either there's a smaller sample size for the females, and or the standard deviation is larger for the females compared to the males. So I could create this. I could go into SPSS and do this. Let's just check our results here while we're doing this. So we got to, where did we get to? We got to, there's the last one, 20 times. That contains 3.33, 3.33, 3.33. It's going up here, 3.33. Let's have a look. Yeah, 3.33. 3.33 within all of these values here. It's number 5 is the only one that fell out. So 19 times out of 20, 95% of the time, the intervals that we calculated captured the true population mean. Now, if we want to calculate the true population mean for our to analyze things like the differences between the average ages, let's say, for males and females in our little employee data set, we could do that. We could go back and go to graphs and call up these error bars that we're seeing here and graph the relationship. We could show the relationship as a chart, or we could go back to what's called the explore procedure, which is under the summarize menu, analyze summarize menu, and it would effectively compare the two averages for us. Okay. Okay, let's take this up to the end there, just so you're aware that there are some further reading that you can do. There's some little blog series that we've got here to work with, and it goes into this in more detail, talks about differences between testing and inferring, what's so standard about a standard deviation, looks at normality, why normal distribution is so important, and lots of other interesting things there. You should also be aware, we recommend this book, a great book by Professor David Spiegelhalter called The Art of Statistics. It's really useful, gentle introduction to statistics and takes you up to all the things that we've discussed here and talks about in detail. You should also be aware we've introduced a new chatbot called ChatSPSS. So this is really useful if you're asking about things like inferential statistics, if you're asking about significance testing and you want to understand the difference between one significance test and another, or you want help with interpreting a significance test. This will be a really good way to do that. You can sign up for it. It's entirely free. You should be aware, of course, that we have a lot of experience in training and consultancy. We provide online training, we provide in-person training, and we also provide a training catalog to our customers. We can help you manage your existing SPSS licenses if you're not a customer of ours, and you can buy your software directly online from us. We also offer no strings attached technical business advice to everybody and all comers, and we also offer formal technical support services around the IBM SPSS product family. The best thing to do is just reach out to us. In the meantime, I hope you found that useful. You'll find a lot of other videos of other webinars that we've done on our website and on YouTube. And you'll also see that we've got a full program of webinars coming throughout the year. So if you want to keep abreast of that, just go onto our website and sign up, and we'll let you know what's coming up in the future. In the meantime, thanks very much for logging in. We look forward to you logging in again in the future.